You step outside this morning and breathe without thinking about it. The sky above you is blue. The air is calm, steady, and completely harmless. You assume the ground beneath your feet has always looked something like this. It hasn't. For most of Earth's 4.5 billion years, standing exactly where you're standing right now would have killed you in under a minute. Not from an accident. From the planet itself. The sky wasn't blue, the ocean wasn't safe, and the air you're breathing simply didn't exist yet. So what did the world actually look like before it became livable? And how did something this hostile ever turn into something this quiet? Rewind to the very beginning, and the story starts with a crash. Roughly 4.5 billion years ago, an object close to the size of Mars, one scientists now call Theia, slammed directly into the young, half-formed Earth. The impact didn't just crack the surface, it liquefied it. Rock stopped being rock and became glowing, molten ocean, stretching from horizon to horizon. Debris flung out from that collision eventually clumped together and became the moon, which means the pale object hanging in your night sky is quite literally a leftover chunk of that catastrophe. Earth itself was left spinning as a ball of exposed magma, with no atmosphere worth the name, no ocean, and no ground solid enough to stand on. Slowly, over tens of millions of years, the surface cooled enough to form a thin crust. It cracked. It reformed. It got struck again. Scientists call this stretch of time the Hadean Eon, named directly after Hades, the underworld. The name isn't poetic exaggeration. Meteors fell constantly during this period, some large enough to remelt patches of crust that had only just finished hardening. For decades, researchers assumed nothing from this era could possibly survive to be studied. Then geologist John Valley and his team at the University of Wisconsin started examining tiny, nearly indestructible mineral fragments called zircon crystals, pulled from a rock formation in Western Australia called the Jack Hills. Zircon can survive melting, crushing, and billions of years of geological punishment. Valley's team dated some of these crystals to 4.4 billion years old, making them the oldest known material ever found on Earth. Trapped inside them were chemical signatures that could only have formed in the presence of liquid water. Some researchers believe the bombardment actually intensified later on, in an event known as the Late Heavy Bombardment, roughly 3.9 billion years ago. The evidence comes from an unlikely place. When astronauts brought lunar rock samples back during the Apollo missions, scientists dating those samples found a strange cluster of impact ages, almost as if the inner solar system had been struck by a sudden spike of asteroids all around the same time. If Earth was hit just as hard as the Moon during that window, and there's no reason to think it wasn't, then even after the crust had cooled and stabilized, the surface may have been repeatedly torn open again by impacts large enough to boil away entire seas. Picture surviving a hurricane, only to have a second one arrive from space every few million years. That was the environment life was somehow about to take root in. Liquid water, on a planet that had just finished being turned into lava. That single discovery rewrote the entire timeline. It meant oceans existed far earlier than anyone had expected, forming almost as soon as the crust was stable enough to hold them. But picturing those oceans the way you picture an ocean today would be a mistake. Imagine something closer to a boiling acidic soup, roiling under a sky that wasn't blue at all. There was no oxygen yet to scatter light the way it does now. Instead, the atmosphere was a thick, hazy mixture of methane, ammonia, carbon dioxide, and hydrogen sulfide, the same gas responsible for the smell of rotten eggs. Depending on the exact mixture, the sky may have looked orange, or a dull, smoky red, closer to a permanent volcanic haze than a sunrise. Breathing that air, even once, would almost certainly have been fatal. Some researchers have taken that idea even further. Planetary scientist Alexander Pavlov and colleagues proposed that methane in that early atmosphere could have reacted with sunlight to form a thick organic haze, similar to the smog-like atmosphere seen today on Titan, Saturn's largest moon. If that hypothesis is correct, Earth wouldn't have looked blue from space at all. It would have looked like a pale orange dot wrapped in a permanent haze thick enough to blur the sun into a dim, smudged glow. You wouldn't have been able to see stars at night. You might not have been able to see much of anything. Here's a strange twist most people never learn. The sun back then was actually weaker than it is today. dimmer by roughly 30% according to standard models of stellar evolution. By all logic, Earth should have been frozen solid. It wasn't. Thick layers of greenhouse gases, the same gases making the air unbreathable, trapped enough heat to keep the surface warm despite the fainter sun. Scientists call this puzzle the faint young sun paradox. And it's one more reminder that almost nothing about early Earth behaved the way you'd expect it to. So how does a planet like that ever produce anything resembling life? In 1953, a graduate student named Stanley Miller, working under chemist Harold Urey at the University of Chicago, decided to find out directly. Miller built a sealed glass apparatus filled with water, methane, ammonia, and hydrogen gas, the best available guess at early Earth's atmosphere. He ran electrical sparks through the mixture to simulate lightning, then waited. Within a week, the water inside had turned a reddish-brown. When Miller analyzed it, he found amino acids, the literal building blocks of proteins, and by extension of every living thing, including you. They had assembled themselves out of nothing but gas, water, and electricity. No life was involved in creating them at all. That experiment didn't prove exactly how life began. What it proved was almost as important. It showed that the raw ingredients for life weren't rare or mysterious. They were an ordinary outcome of basic chemistry, given the right materials and enough time. And early Earth had both in enormous supply. Lightning struck constantly in that unstable, churning atmosphere. The oceans acted as one uninterrupted chemistry experiment, mixing and remixing across hundreds of millions of years. At some point in that process, in a way scientists still can't fully explain, chemistry crossed over into biology. The earliest organisms looked nothing like anything you'd recognize as alive. No visible movement, no nucleus inside their cells. Just simple, single-celled microbes, likely clustered near underwater volcanic vents, feeding on chemicals seeping up from the planet's molten interior instead of on sunlight. Extremophiles like these still exist today, thriving in places like the boiling hot springs of Yellowstone, and they're considered close living relatives of some of the very first life on Earth. For close to 2 billion years, this was the entire story of life on the planet. Microscopic. Invisible without a microscope, humanity wouldn't invent for billions of years, and still breathing absolutely nothing like the air filling your lungs right now. Then everything changed, and not because of a meteor or a volcano. It changed because of waste. A group of microorganisms called cyanobacteria evolved a new trick, pulling in sunlight and converting it into usable energy, a process called photosynthesis, while releasing a leftover gas as a byproduct. That gas was oxygen. To modern ears, oxygen sounds like a gift. To nearly everything alive at the time, it was closer to poison. Almost all life on Earth had evolved in a world completely without it, and oxygen is a highly reactive molecule, capable of tearing apart the delicate chemical structures early cells depended on to survive. As cyanobacteria spread across the oceans over hundreds of millions of years, oxygen began accumulating first in the water, then in the atmosphere above it. You can actually see the evidence of this event preserved in rock today in layered red and gray stone called banded iron formation, created as oxygen reacted with iron dissolved in the ocean, causing it to rust and sink to the seafloor in visible stripes. How do scientists even know oxygen was missing in the first place? Part of the answer comes from sulfur. Geochemist James Farquhar at the University of Maryland studied the way sulfur atoms found in ancient rock had split apart under ultraviolet light in a very specific pattern, one that only happens when there's no ozone layer filtering that radiation out of the sky. Below a certain point in the rock record, that pattern is everywhere. Above it, the pattern vanishes almost overnight, geologically speaking. That single shift in the chemistry of sulfur is one of the clearest fingerprints scientists have for the exact moment breathable air started to exist. Around 2.4 billion years ago, oxygen levels rose high enough to trigger what scientists now call the Great Oxidation Event. Researchers sometimes describe it, only half-jokingly, as Earth's first mass extinction. Organisms that couldn't tolerate the new gas were wiped out on a massive scale or forced into hiding in oxygen-free pockets of mud, sediment, and deep rock. where their distant descendants still survive today. Isn't it strange that the exact gas keeping you alive right now was once considered an existential threat by nearly every living thing on the planet? There was an unexpected upside buried inside that disaster. As oxygen built up in the atmosphere, some of it drifted higher and reacted with sunlight to form a thin protective layer of ozone, a gas that blocks deadly ultraviolet radiation from reaching the surface. Before that layer existed, UV radiation would have shredded the DNA of anything attempting to survive on dry land. Once it formed, it acted like a shield, and life slowly gained the option of eventually crawling out of the ocean altogether. None of that would have been possible without the very gas that had just wiped out most of the planet's existing organisms. Even after the Great Oxidation Event, the story didn't move quickly. Oxygen levels rose, then stalled, sitting at a low, stable level for well over 1 billion years, a stretch of time some geologists have nicknamed the Boring Billion. Complex life barely progressed during this window. Nothing much larger than a single cell existed. It's a useful reminder that evolution isn't a straight climb towards something like you. For over 1 billion years, the planet's most advanced life form was still, essentially, pond scum, quietly waiting for conditions to shift again. Earth still wasn't finished being hostile. Long after the atmosphere started resembling something breathable, the planet nearly froze solid, more than once. Geologist Paul Hoffman, working at Harvard, spent years studying glacial deposits found in tropical regions, layers of rock that could only have formed if ice sheets had once reached all the way down to the equator. His research helped establish what's now known as the Snowball Earth hypothesis. Somewhere between roughly 720 and 635 million years ago, evidence suggests the entire planet, oceans included, may have frozen into a single ice-covered sphere. That much ice would have reflected sunlight straight back into space, locking the planet into a deep freeze lasting millions of years. What finally broke the cycle wasn't the sun. It was volcanoes slowly building up carbon dioxide beneath the ice until enough of a greenhouse effect accumulated to melt it. When the ice finally cracked, many researchers consider the resulting explosion of life that followed to be a direct trigger for the rapid diversification of complex organisms in the ages after. Not long after that final thaw, in geological terms, the fossil record shows something unprecedented. Within a few tens of millions of years, an evolutionary event known as the Cambrian explosion produced an explosion of body types that had never existed before. Shells, eyes, legs, predators, and the defenses built to survive them. Almost every major animal group alive today can trace its basic body plan back to that single burst of diversification. A frozen, nearly lifeless planet had, in a geological blink, become the ancestor of a world crawling with complex, hunting, fleeing, evolving creatures. Stop and add all of that up. A molten surface, a toxic orange sky, boiling acidic oceans, a poisonous new gas wiping out most of the life that existed at the time. A planet frozen solid from pole to pole more than once. If you had been dropped onto Earth at almost any point during its first 4 billion years wearing nothing but the clothes on your back, none of those environments would have let you survive past a few minutes. Here's the part that should genuinely unsettle you. You're not separate from any of that history. You're built from it. The mitochondria inside nearly every cell in your body, the tiny structures responsible for converting oxygen into usable energy, are widely believed by biologists, following research first proposed by biologist Lynn Margulis, to have originated as free-living bacteria, engulfed by a larger cell roughly 2 billion years ago. Instead of being destroyed, they were kept, absorbed into a partnership that eventually became every complex organism on the planet, including you. Every time you take a breath, descendants of ancient bacteria that learned to survive Earth's first toxic gas are still, quite literally, doing their job inside your cells, converting that same oxygen into the energy keeping you alive right now. So the sky is blue now because oxygen scatters sunlight that particular way. The oceans are stable now because the bombardment ended billions of years ago. The air is breathable now because of an ancient poisoning event that wiped out most of what came before you. None of it was inevitable. None of it happened gently. It looked closer to a repeated demolition and rebuild, stretched across billions of years, with your existence sitting on the far end of it as an almost accidental byproduct of the wreckage. Think about that the next time the sky looks ordinary to you. It isn't. It's the surviving settlement of a war fought over billions of years, one your body is still quietly a part of. You step outside again. You breathe without thinking about it, but that breath was never neutral. It's the tail end of a 4 billion-year chemical war, one your ancestors' survived, adapted to, and eventually turned into the very thing keeping you alive today. The ground under your feet was never simply your home. For most of its existence, it was closer to a terrifying alien world, one that, given the smallest opportunity, would have erased you instantly. You just happened to be standing here after it finally, slowly, stopped trying to. And somewhere inside you, in every cell doing the quiet work of keeping you alive, that history is still running.